To really describe the difference between Euclidean geometry and non-Euclidean geometry, we have to first understand the four axioms that Euclid initially came up with in geometry. The four axioms are basically: a straight line can be drawn by connecting 2 points. Any straight line between 2 points can be extended an infinite distance in either directions. Circles can be drawn with any points at the center and any radius. And all right angles are measured 90 degrees and are identical to each other. In addition to these four axioms, Euclid came up with a fifth axiom that defines the difference between Euclidean, hyperbolic, and elliptic geometries. Euclid's fifth axiom states that if you have a straight line and a point outside of that line, there's only one straight line that passes through that point and is parallel to the first line. This would later be known as the parallel postulate. However, the thing about this axiom that people ended not liking was the fact that it was too long and it was too much like a theorem. Theorems are similar to axiom, but instead of being self-evident and easy to recognize, they have to be proven with theorems, a combination of axioms, and logic. So people tried to prove the fifth axiom for many years using the other four axioms, but no one really managed to do it. Hundreds of years later, Girolamo Saccheri tried to prove the fifth theorem by contradicting it. He drew up two pairs of parallel lines that intersect to form a quadrilateral, and say that the two opposite corners were 90 degrees. That means that the remaining two angles had to be less than 90 degrees, exactly 90 degrees, or more than 90 degrees. Since the angle measures of all quadrilaterals add up to 360 degrees, the obvious conclusion was that the other two angles also had to be 90 degrees, and Saccheri left the problem feeling that he has solved it. After that, several years later, Johann Lambert picked up where Saccheri left and took a second look at the three possibilities he came up with. At first sight, it seemed obvious that the remaining two angles had to be right angles as well. But the curious thing was that even though it wasn't possible for the angles to be greater or less than 90 degrees, those two answers couldn't be disproved either. After a lot of time passed and several people messed around with the possibilities of ignoring Euclid's fifth axiom, mathematicians came up with names for them. So we have Euclidean geometry is what we are familiar with on day-to-day basis and follow Euclid's parallel postulate. That is, given a straight line and a point not on the line, there is only one line you can draw that passes through that point and is parallel to the first line. We have also hyperbolic geometry that can be derived from the answer to the Saccheri's quadrilateral where the two remaining angles are smaller than 90 degrees. It's typically only used to very high-level math and physics and some models of the universe. We also have elliptic geometry that is derived from the last answer to Saccheri's quadrilateral, where the two remaining angles are larger than 90 degrees. Unlike hyperbolic geometry, elliptic geometry is widely used by pilots and ship captains because it describes the geometry on the surface of spheres. Similar to Euclidean and hyperbolic geometries, it too has its own variation on the original parallel postulate, which states, given a straight line and a point not on the line, there are no lines parallel to the initial line. So bottom line, we have that Euclidean geometry has one parallel line passing through any given point not on a line, hyperbolic has at least two parallel lines, and elliptic has no parallel lines.